I'll mute my mic, I might mute her mic. I'll try.
Good afternoon, everyone. My name is Marine Favre-Declos, and I will be presenting the RDM webinar this afternoon.
Okay.
We are going to start with a short presentation on Genesis, but then we'll go straight onto the RDM method. We'll try to understand how RDM works through an example on a body and white. We'll then see two other applications on a tailgate assembly and a very simple example on a stool. This presentation should be around 30 minutes. We'll then have 15 minutes questions at the end. Regarding Genesis, as an overhaul, it is an Nastron-based solver. It can do static analysis. It deals also with contact analysis, linear buckling, heat transfer, and so on. There is no additional cost when using the parallel solving, and it also includes a very fast SMS eigenvalue solver for static analysis. Genesis optimization capabilities are very large. You can use different methods. You can also combine this method. The most common ones are topology optimization, which works on the density of the elements. You have also sizing optimization, which is the panel thickness optimization. Topography optimization gives you the optimized pattern on a surface. You have then shape optimization, which works on parameters. Topometry optimization works also like sizing, but on different elements patterns. And finally, composite optimization. Looking at the reinforcement derivation method, the goal of the RDM is to quickly identify optimal load path for any component that is defined as solid elements, or you can also identify reinforcement pattern for shell elements, as you can see on the left-hand side. To do this, the user creates material, shell or solid, in the design region, which is then automatically connected to the existing structure. Moving on to a clear example, which is a body and white. The first approach, if you want to optimize the structure, could be to use topology optimization. But as you can see, topology optimization results are really organic shapes, which is very difficult to interpret into manufacturable parts. It has also some package limitation, and you never really work from a blank page. So usually most of the sections are carryover from the previous vehicle. That's why topology optimization is not the most suitable solution here. To illustrate the capabilities of RDM, the best is to look at a project we did a couple of years ago on the Ford Fiesta. So we had the vehicle in the FE model, and we wanted to optimize two load cases. The first one was the first mode of frequency. So we tried to increase this first mode as high as possible, and also improve the torsional stiffness regarding the static torsion load case. This is our starting point. So this is the baseline, the body and white as we received it. We then have created RDM region around the structure, which has been automatically connected to the body and white. After running the optimization for the two load case, so model analysis and static torsion, Genesis has removed the superfluous material and leave only the most important parts. So all the red parts that you see is the material that Genesis wants to keep. And this clearly identifies the weakness of the body and white. But obviously this is not the solution. You need then to interpret this results onto something manufacturable. So this is what we did with mainly three options. The first one, when we have a very small amount of material, this can be interpreted as Spot-welds, which has the main advantage to don't add any mass to the structure and also is quite low in cost. The second option is to modify existing parts to improve the load flow between those parts. And finally, the other solution is to add a new component that was not present before the RDM, which usually improves a lot the stiffness, but then will also add some mass to the structure. Alright, let's have a look in detail to the RDM results and the interpretation we did from it. First of all, we have created 10 spot-welds where a bit of materials were on the structure, which has improved the stiffness by 1% without adding any mass. So this is a quick way to improve stiffness without almost any modifications. Looking at the lower corner of the boot aperture, we have tried to improve the connection of the inner back panel onto the longitudinal one in order to improve the load flow between those two parts. This has increased the first mode by 5%, but has increased the mass only by 0.5%. Looking at the upper corner of the boot aperture, we have in the same way tried to improve the load path between those two parts. This has increased the first mode by 30% without almost adding any mass. Finally, looking at the rear suspension turret top, you can see that there is some material there that is trying to connect the turret top to the back panel. So because of this, we have added a new part which has increased the first mode by 23% but added 1.2 kilo to the structure. And the funny thing is, when we were doing this optimization, the body and white that we had was the Fiesta from 2002. And if we look at the Fiesta from 2008, you see the exact same panel that we were trying to add onto the new body and white. So we were not that far from the good solution. To summarize what we did for this study, we have succeeded to improve the first mode by 43% and the static torsional stiffness by 68%. this has cost us an additional 7.5 kilogram. So you could argue, okay, this is good work, but we all know that we would like to reduce the mass, so adding 7.5 kilo is not the best idea. So because of this, we did then a gauge optimization, which means that we try to improve the thickness of each of the panels, try to reduce the thickness when it's not necessary. We have then divided the panels in 3 categories. So the blue panels have a thickness that can increase and decrease. The red one, the thickness can only increase because they are quite important panels, for example, for crashworthiness. And finally, the panels that have a thickness that cannot change, for example, the body side panels or the panels that have a surface that is necessary, we have then removed it from the optimization. This is the thickness change that we obtain after the optimization. And you can see when you compare the first torsional mold that we are almost identical to the solution when after modifying the body and white, but with a decrease of mass that is quite important. In fact, we have improved the performance, but also we have reduced the mass compared to the baseline. So this is one example that we have seen on the body and white. But as you can imagine, the possibilities are endless. You could use this for plastic parts or gearbox casing, but obviously you can use this for non-automotive applications. For example, this is what we did on a tailgate. So this is a rear tailgate. The goal was to determine the optimal reparting of a stool, of a tailgate, sorry, the internal reinforcement. So we have some constraint, obviously. Here on the right, the translation on the X and Z axis have been restrained, whereas on the left, the rotation on the vertical axis is allowed only. And 3 static torsions, static load case, sorry, have been defined, the vertical, lateral, and fore-aft. We have then created inside this tailgate the RDM. So we have used the wrap option, which means that we are going to put material inside the existing structure. The target mesh size is the same as the existing FE model, and we put the offset distance from the back panel. We create solid elements still, which is fine. And as you can see, the RDM is automatically created inside the structure. If we make the structure transparent, we'll see a bit more what's happening inside. Okay. So once the RDM is created, you have these green connections that are automatically created between the RDM and the structure. For this example, we don't want the RDM to be rigidly fixed to the structure. We want only the connection to be made between the RDM and the pads on the sides. So we delete this connection and we are going to create new connections with thanks to two sets of nodes. The first set of nodes contains all the nodes from the pads, so we select all these nodes. And the second set will contain the RDM region. Thanks to an add-on plugin that GRM has developed, we can create automatically new connections, so we'll create rigid connections from these two sets that we previously created. So as you can see, the two parts are now connected. We can now save the optimization and start running it. It will take a couple of minutes, and finally we'll have the last cycle. We just need to import the results. So in this example, we run the optimization locally, but it will work as well if you run it on a cluster. And we can check the RDM results. That's it, as simple as that. So we clearly identified the load path for this 3 load case. So where the material is where the load is going from one pad to another. All right, let's move on to another example. We have seen 2 examples of automotive application, one on body and whites, one on a tailgate. We'll see now an example of an armrest. This is a train seat armrest that we developed this year. You can see that we have a casting type of armrest. The user can then define the rib pattern that he wants to create with different manufacturing constraints. And after running the optimization, the best rib pattern appear. All right, let's have a look to this tool. This is a very, very simple example, but I think it makes it a bit more clear that RDM is finally a simple thing and it doesn't need to be complicated to work. So we had an initial rib pattern, the simplest one that can exist, which is obviously not optimized. And our goal is to optimize this rib pattern for a 2 kilonewton load case. So the baseline performance that we are seeing now, we have vertical displacement of 1.1 millimeter, and our goal is to optimize the rib pattern, but keeping the same performance as the baseline. First of all, we are going to delete these existing ribs. So we select the ribs one by one. So I'm going to pass this. And once all is selected, we can delete these ribs so as to create the new one. Okay. So moving on to the plugin in GRM Toolkit, we select the RDM button, and we are going to use the projection tool. So projection is because we create ribs by projection of the seat element onto a certain direction. So in this case, the projection axis is the y-axis. And we want the ribs to be 37 millimeter long. We select the shell element type and different ribs pattern that we want with the pitch that is desired. And finally, we'll define the material for the ribs, which is nylon in this case. And that's it. This new rib have been created. Obviously, we don't want all of it, so we are going to delete all the ribs that are unwanted. Even if we select all the elements, only the elements that are from the RDM region will be deleted, not the structure. We can then define the fabrication constraints. We want something manufacturable, so we want to put a casting constraint from top to bottom, so that the material will be kept at the top of the seat and be removed at the bottom. We want to maximize the stiffness by using only 30% of the initial mass of the ribs. This final step has for goal to define all the optimization setups, so the number of CPU, the memory that you want to use on your computer. And then we are ready to run the optimization. It will take a couple of minutes, and at the end we'll be able to bring the last cycle results. And review the results of the optimization. So this is the optimized rib pattern. This is how a stool should look like. And we can double check the performance of this optimized stool, which is identical to the baseline. All right. This example ended the presentation. I think you've all understood how easy RDM is and how quick it can give you first the load path, second the rib pattern, and it is a quick way to understand where material is needed, where material is not needed, and how to improve the stiffness of your structure without increasing the mass too much. All these tutorials are in our YouTube channel. If you just type GRM Consulting, you will have lots of videos involving RDM, but not only. You have also composite optimization tutorials. You have also SolidWorks tutorials. Anyway, have a look to our YouTube channel. I think there's some useful things. All right. Well, I have finished with the presentation, but we have some time now for questions. So please don't hesitate to write me some questions, and I'll be happy to answer it straight away. No questions for now. Okay, well, anyway, I think you all have my email address, or at least Martin's email address. So anytime you have a question regarding RDM, regarding Genesis, or either on tutorials or on your own projects, I'll be very happy to help you as much as I can. And if I don't, I'll just ask Martin, and for sure he will find a solution. All right, so thank you all for your attention. I hope you have no secret with RDM, and I hope to talk to you soon. Thank you. Bye.